Boom. Hello and welcome back to Calculus 1, section 3.3, Rules of Differentiation. Yeah. So let's talk about notation first and words that we are using. So what is the meaning of the word differentiation? Differentiation means take the derivative of the functions. It's a process of taking the derivative. So differentiation is the process of taking the derivative. Sometimes down the line we will say function is differentiable, which means that you can take the derivative of that function. So differentiation is the process of taking the derivative. And we already talked about the notation for the derivatives. We know that we can write y prime, f of x prime, dy dx, and those are the ones that we use most of the time. Now, out of all, the best notation is dy dx. You can also call it df dx, and that's Leibniz notation. We are going to see down the line why is this notation superior, but others are okay as well. So far we also learned that the way to take the derivative is to do that limit. So f prime of x was defined as the limit h goes to 0 of f of x plus h minus f of x divided by h. And this was the formula that will compute the derivative. We also know that the derivative function is the function that generates all of the slopes of tangent lines. And those tangent lines are measuring the change because they're slopes. The tangent lines measure the change as we observe a system that is evolving. But we also seen that these calculations tend to be a little bit long and tricky. So now you are faced with a choice like the choice that was presented to you a long time ago, except people didn't put it as a choice. They said, learn this. At some time, a point in time in your past, 3 plus 3 plus 3 plus 3, you learned that to be a 15. And then you said, well, let me memorize 3 times 5 is 15, because it's really annoying to compute 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15 every time when you need to calculate something like that. So someone told you that it's a good idea to memorize multiplication table so that you can avoid repeated addition, which really comes in handy if you have, let's say, 49 times, let's say, 13. That will be 49 plus 49 plus 49 plus 49 plus 49 plus 49, right? And then you have to calculate all of that. Instead of say, oh, okay, 3 times 9, and right, and you do the multiplication over here. Here. Now, you are going to be, now you are facing the same choice. You have the formula that computes the derivative. That's that. And that works. Can we compute these derivatives faster if we memorize certain rules? So the jump from repeated addition into multiplication, or the jump from repeated multiplication into exponents, is repeating again, except now we are going to memorize formulas for derivatives, and then you will never have to use the limit definition again. So let's memorize the formulas, if you're interested. So the first formula to memorize is the formula which we mentioned last class when we talked about those graphs. We said that derivative of a constant is 0. Remember, there is a 0 change in a constant because it's constant. So since there is no change, its derivative is 0. So the first formula we are memorizing is that the derivative of any constant is 0. Which means that the derivative of number 5 is 0. The derivative of pi is 0. The derivative of technically any number you can come up, well, let's do negative 19/3 is also 0. So derivative of the constant is 0 because there is no change within a constant. Now we move to the next formula that we need to memorize, and that is the derivative of x to the n is equal to n x to the n minus 1. This formula for taking derivatives is covering a lot. It's definitely covering the derivative of x squared, right? But it also covers the derivative of square root of x, and it also covers the derivative of 1 over x to the 8 and stuff like that. So let's talk about it. The derivative of x to the 8 is equal to, well, we see that n is equal to 8 in this case, so it's 8, x to the 8 minus 1 is 7. Imagine doing this with a limit. Yes, you have x plus h to the 8th, then you go the Pascal's triangle to get the coefficients. You get something that even when you flip the notebook sideways you can't write. And then subtract, collect the terms, factor out h. You are going to get this as a result, but it's going to be really long. What happened? I did this. For n is equal to 8. Because n is 8. You drop n down, and then n minus 1. The derivative of square root of x. Well, that can be also written as the exponent. It's a 1/2, right? Anyone? Hi. Oh, you're here. So much enthusiasm tonight. 1/2 x. Negative 1/2. Because 1/2 minus 1 is negative 1/2. We are going to write this as 1 over 2 root x. It is okay to leave square root of x in denominator because we don't know what x is. Could be 3. You have to rationalize once you plug in 3. But it also could be 4. And in that case, you don't have to, right? The entire thing is 1/4. So you do not have to rationalize this root x. You can leave it as is. And the last one over here is 1 divided by x to the 7th, which you can also rewrite as the derivative of x to the negative 7, which gives us negative 7x to the negative 8, which gives us negative 7 over x to the 8. So this is in one spot the use of the entire the use of the formula which covers a lot, the polynomials, rational functions, and radical functions at the same time. One rule covers them all. It's just your job to know the algebra to rewrite these particular expressions so that you can use the formula to take the derivative. Now, each one of these calculations used to be almost a page, right? Now, you look at it and you just write the answer. What's the trade-off? You have to memorize the formula. Now, obviously, the honors calculus is going to take a look and prove the formula, use the binomial expansion, and so on. But, right, that's the honors portion. So, these two formulas cover a lot. Derivative of a constant and derivative of x to the n, where n could be positive, negative, or a fraction. So now, say that you have a problem which says what's the derivative of, and you are looking at uh, 1 over cube root of x to the 5. What would that derivative be? What is the first thing you need to write? Yes? Okay, so the first, okay, we can do that. So 1 over 5, x to the 5/3. And then what? Bring it to the top. You could have done it in the same, but that's okay. So negative 5/3. And now you unleash the formula. Negative 5/3 x to the negative, very good, is equal to negative 5 over 3 cube root of x to the 8. So, where's my screen? Just want to make sure if anyone opens the door. That works. Good. All right, we're safe. So we have the derivative of the constant is 0 and derivative of these x to the whatever exponent n, right, to be given by n times x to the n minus 1. So we're just subtracting 1 on the exponent every time. The next rule is labeled as, I guess, a quality of life rule, where we take the constant and we can kick the constant outside of the differentiation, just like we did in limits. So if you are taking the derivative of constant times some function f of x, you can kick the constant outside and then just focus on the derivative of the function. So this is, I label this as a quality of life formula because it helps us solve the problems. So let's say you have the derivative of 3x to the 9th. Well, we know how to take the derivative of x to the 9th. We don't know what to do with 3 yet. And that's what the rule helps us with. The rule tells you that you can kick 3 all the way outside and then focus your derivative only to x to the 9, which is our good old x to the n rule. So copy 3 times, and then we have 9x to the 8 for the total of 27x to the 8. Now, I understand that you will, within a week, go from here directly to the end result. Whatever we have in between, right in the middle now, is for you to learn the rules and concepts and start somewhere. So you have what's going to happen within a week for all of you guys. 9 times 3 is 27, x to the 8, which is exactly the end result. Also, I will star this problem, next problem, because a lot of confusion happens eventually. Say you have 5 over x to the 4th. See, right now it's clear to you what you are supposed to do. But then when you learn a little bit more, you start doing something that it's extra calculations for no reason. What we know over here is that we can kick 5 outside in front of the derivative. And then we're going to just focus the derivative on x to the negative 4th. So now I have 5 times negative 4, x to the negative 5, and then finally negative 20 divided by x to the 5. This is the fastest way to do this problem. We are going to learn something that's called the quotient rule, and if you use the quotient rule on this problem, you are going to spend a lot more time and energy to get the same answer at the end. So this is the fastest way to deal with these types of problems. So this rule is what we call the quality of life rule, okay? We don't have to worry about, in these cases over here, about 3 and a 5. We kick those outside in front of differentiation, and we differentiate the function, right? Take the derivative. Remember, the word differentiation means take the derivative. So you take the derivative, and then just multiply that constant back into whatever answer you have. More rules. The derivative of the sum of two functions, or the difference for that matter, let's do sum only, is equal to derivative of f of x plus separate derivative for g of x. And then write the same formula for a minus underneath. And I will also box this blue. More quality of life, I guess.
So this is the same as the difference law that we wrote about?
The difference law for limits, yes.
Oh, that's for limits. This is the...
Well, this is for derivatives, but they look the same because they are the same. Remember that limits define derivatives, right? So not all, but most of the properties propagate forward. Well, not most, just few. The ones that I wrote. Multiplication, division, squaring, they don't work. All right, so now what is this quality of life over here? Well, if you have multiple terms, you know that you can have the derivative of function x squared plus, let's say, plus x minus 1. This is a trinomial, and it has 3 terms. So these formulas above allow us to take independent derivatives of each one of these terms. So again, you will not be writing these steps in a future, but right now to learn, it's good to write them. So individual derivatives for each one of the terms, keeping the signs in between. So what do I have? I have 2x plus 1 minus 0. So it's 2x plus 1. The derivative is 2x plus 1. Again, you don't like these rules? Go ahead, have fun with the limit. And now I'm going to ask you to work out on combine rules. So say that find the derivative of 3x squared plus 9x minus 6 over x squared. So what is this derivative? All right, so we do the separate derivatives and kick the constants outside. So we have 3, the derivative of x squared, plus 9, derivative of x, and then minus 6, the derivative of x to the negative 2. So that is going to give us 3 times the derivative of x squared is 2x, plus 9 times the derivative of x is 1, and minus 6, the derivative of x to the negative 2 is negative 2x to the negative 3, using the x to the n formula. So all together over here, 6x plus 9 plus 12 divided by x cubed. And that would be the answer. I think it is. Negative 6 times negative 2 is positive 12. Unless the rules have changed. For those of you that are questioning now and not asking, why is the derivative of x equal to 1? Well, the derivative of x is actually the derivative of x raised to the first power, and that is going to be 1 times x to the 1 minus 1, which is 1 times x to the 0, which is 1 times 1, which is 1. Right? So we are still using the same 1 to the, so x to the n rule. And as soon as we realize that x is actually x to the first power, the rest is just subtracting numbers and so on. We have one more formula for derivatives to learn now. We're not doing any trig tonight. There will be a section for trig and a section for inverse trig. Those are later in the section, in the chapter. Now we're only going to take a look at the derivative of e to the x is itself e to the x. So this is the only function that does this. The derivative is the same as the function. Everything else is something different. And also, we have to know it for now, but we are going to learn technique to deal with this. E to the ax is a e to the ax in a derivative. So these are the derivatives of exponential functions with base e. We will deal with the non-e bases later again. So these are the basics. So a problem for you to practice. What's the derivative of 3x squared plus 9 plus 4e to the negative 2x? Talk to people around you. Make sure it's going well. What happened?
You know when you take out the 4, and then you have the negative 2, e to the negative 2x. Is it like that way?
Oh, you're right. So that, yeah, that's 0. I'm not sure about the 9. I'm not sure about that.
All done?
Yeah, multiply that by 4, so you get negative 4.
Well, you can see, look at it first.
Yeah. Where's your e? No. The last time I was.
Yeah, we did the equal.
Yeah. Go back.
Go back. Oh, shit.
Go back. Oh, that's a.
I shoot.
Oh, yeah, yeah. Then it's a quarter then. All right. So, guys, let's go. Again, this step you might be skipping in the future, which is okay. 3 derivative of x squared plus the derivative of 9, which we know it's what? 0. And then plus 4 times the derivative of e to the negative 2x. So this is just rewriting so we can use our basic rules. 3 times 2x plus 0 plus 4 times, and using this formula here, we have a negative 2 times e to the negative 2x. So now that's equal to 6x, 0 is gone, minus 8 e to the negative 2x. Yes.
Why is the derivative of 9 0?
9 is a constant, right?
So it's just 0. Change.
Very good. There's no 0. The derivative is 0 because there's no change in 9, which is a constant. Good. All right. Yes. You can write this as 8 over e to the 2x, but yeah, yeah. Sense the tone. Tangent lines. Tangent lines. Tangent line is the central problem of Calculus 1. Tangent line is the one whose slope measures the change at the point. At every point of the function, tangent line changes to adjust itself, obviously, unless function is constant, in which case the slope of the tangent line is always 0. But if you have, let's say, a function that is like negative x squared, we have all of these different tangent lines that we can draw. All of these tangent lines happen at certain x values, and they all, as you can see, have different slopes because, right, different value brings out the different derivative, which is the slope. So now we are going to work on this problem, and then you are going to start this problem because this is going to be the most important problem of the entire course, finding the tangent line. Every single section of chapter 3 will have the problem which says find the tangent line, because we are going to learn different methods of differentiation, so it doesn't matter really which thing you use. Let's see what this means first. So we learned so far that the slope of the tangent line is the derivative computed at value that we want. So this is at x equals a. So now let's have a problem. Find the tangent line for, let's say, f of x equals x squared minus x plus 3 at x equals to 4. Okay. What do I have? Well, first of all, from here, I see that a is 4, because this is the point at which I am going to look for the tangent line. So that slope and everything else. All right, to find the slope, so to get m, I need f prime of x first. So this is in the solution. Okay, so what's f prime? Eventually. Maybe. I'm just looking for the derivative. So now I have 4, 15 as a point, and I have the slope m equals to 7. You can... Oh my God. So they're looking at, they're watching the stream in the classroom next door, and they came out with a big paper, your stream is down. Anyway, hopefully it's up. We'll see. So now what do I do with this? You can use y equal mx plus b, or y minus y1 is equal to mx minus x1, either one of the two, to calculate the slope, to calculate the equation of the line. So what I'm going to do is I'm going to do both, because I'm a boss. If I use point and slope in the y equal mx plus b, y is 15, m is 7, x is 4, and I'm looking for b. So 15 is equal to 28 plus b, and b is equal to negative 13. So what is the equation of the tangent line? It's y equals 7x minus 13, and that's the answer. That's the tangent line. If you want to use the other formula, well, you leave x and y alone, and you plug in your point for x1, y1. So y minus 15 is equal to m x minus 4. That's y minus 15 is equal to, sorry, m is 7, thank you. 7x minus 28, add 15 to both sides, and there you go. 7x minus 13 again. I don't care which algebra formula you are going to use to come up with a tangent line. The important aspects of this problem are: you will find the slope, you will find the slope m when you plug in the value into the derivative. So m is calculated by plugging in your value, x value, into the derivative. And that gives you the slope. When you plug in your x value into the function, you get y. So all you need is a function and x coordinate. You can calculate y coordinate because you have y equal f of x, and you can calculate the slope because slope is equal to the derivative computed at that point. So you will compute both of these things. You have your x, which is 4. You just computed the y for it, which is 15. And you have m is 7 that you get from the derivative. Which steps you're going to use to get the line? I don't care. Yes? Is the derivative of the function, x squared minus x. Right? Using the rule that we just learned this class. So now, let's have one of these for you to enjoy. Find the equation of the tangent line. Find the equation tangent line at x equals 0 for f of x equals x cubed plus e to the 4x. Or why is the stream down? Hello and welcome. I'm just kidding. This is part 2. Part 2. Let's see. So part 2 of 3.3 rules of differentiation. They're next door watching this live. All right. So what do we have? Encoding overload, consider turning down video settings. No. We'll restart later. It's alive. All right. So here we have our standard procedure. To find the slope, I need the derivative. So the first thing I do is I compute the derivative in respect to x. The derivative is 3x squared plus 4e to the 4x using the rules we just learned in this section. The n-1 rule and the one for e's. the next step is to compute the slope by plugging in the number 0 in this case to figure out. So we plug 0, I get 3 times 0 squared plus 4 times e to the 4 times 0. And what I get is 0 for the first one, right? That gives me 0. This is also 0. E to the 0 is 1. So what I have is 0 plus 4 times 1, and the whole thing is 4, so slope is 4. We calculated slope as 4. So now I have slope and I have x coordinate. The next part is to calculate the y coordinate, which is just f of 0. That is plugging in everything in the original problem. So that's 0 cubed plus e to the 4 times 0, and the whole thing is 1. So now I have a I have the specs, right? Slope is 4 and the point is 0, 1. And now pick your poison, right? Whatever you guys want, point slope or the regular y equal mx plus b slope intercept form. It doesn't matter which one you do. I'm actually using the point slope formula because I rarely use it. For x plus 1? Great. All right, so now this is very important, guys, to realize here. Observe that I took the derivative, right? That's the part that it's going to change from section to section. Everything below stays the same. So you are going to have a basic derivative, which is what we did tonight. You are going to have product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation, all of these different methods to take the derivatives from chapter 3. What they impact is this line, where you take the derivative. So you look at the function, and you will be deciding which method is appropriate to take the derivative. Once you have the derivative, steps for tangent line are the same. Compute the point in your derivative to get m. Compute the point in your original function to get y. You have m, x, y, and in whatever way, right, plug them in with one or the other formula, plug them to find the tangent line. So that's it. This problem will stay unchanged throughout entire chapter 3 and 4. The only thing is type of function will govern which derivative, and we learn different types of derivatives techniques in different sections. So that's the tangent line bit. And the last thing we are talking about in this section are higher order derivatives. Higher order derivatives, meaning second derivative, third derivative, fourth derivative, 104th derivative, and so on. So we start by understanding that we have f of x, which is actually original function, which is the 0th derivative, because no derivative is done on it, right? So that's technically 0th derivative. And then we have f prime of x, which is called the first derivative. We have been dealing with that one so far. Then 2 primes would be the second derivative. 3 primes will give us the third derivative, and then notation switches. So we don't want to be sitting there counting little tick marks forever. Notation changes into this parenthesis around, so it's not confused with exponents. 4th derivative, 5th derivative, going on forever. So note the parentheses around the order of the derivative so it's not confused with exponents. All right, so this is the first derivative, second derivative, third derivative, fourth derivative, fifth derivative. In order to progress through derivative orders, you have to have all previous derivatives. What is the fourth derivative? Fourth derivative is the first derivative of the third derivative. So in order to come up with the fourth derivative, you have to have the third. But to get the third, you have to have the second. And in order to have the second, you have to have the first. And in order to have the first derivative, you have to have original function. So all previous derivatives need to be known. Unless you're dealing with e to the x. What is the 100th derivative of e to the x? E to the x, it's itself, right? If you start with e to the x, the first derivative is e to the x, and then the derivative of that is also e to the x. So all derivatives propagating down will be e to the x. So let's take a look at the problem. Find second derivative. Notation is either f double prime of x or d squared dx squared, because it's the second derivative. For function f of x equals 3x squared plus x minus 11. All right. If I need a second derivative, I have to get the first derivative first. So f prime of x is 6x plus 1. Are we all green on 6x plus 1? Derivative of negative 11 is? Because it's constant, there is no change, therefore 0. And we'll have calculus 2. I'm not letting you go. And then the second derivative is the first derivative of the first derivative. So what would that one be? 6. That's it. What's the third derivative? Third derivative is 0. How about 17th derivative? They will all be 0 after the first time you hit 0, all of them are 0. Now, we are going to have a use for first, second, third derivatives and so on. And we do need to know how to take these derivatives. So now let's have a spicier example for you, and that's it for today. All right, so what's the second derivative? So find the second derivative for f of x equals square root of x. There's a lot of party over here for the second derivative of square root of x.
Missing out.
That's another donation over here. So first, the derivative first. We have f of x prime is equal to, we know that this one is x to the 1/2, right? So we have 1/2 x to the negative 1/2, which is 1 over, oh, sorry, don't fix it, because it's already in a form where you can go and take another derivative. Don't fix it. So now you have copy the old half, drop the new negative half down, and x to the negative 3/2, because negative 1/2 minus 1 is negative 3/2 when you do the common denominator and all of those wonderful things that you're used in algebra. So f double prime, the second derivative of x, is equal to negative 1/4, and you have x to the 3/2 in denominator. So maybe better if we write it this way. There we go. There you go. And this would be our second derivative. Now I just want to show really quick notation-wise if the Leibniz notation pops up in your homework, so you are not confused. We all know that we can write the derivative of x squared in line and get 2x, right? Actually, let's go with a cube. X cubed is 3x squared. I can ask also in line for the second derivative of, let's say, x cubed. Now, observe over here what I have. I have d squared, well, that's d times d, right? And I have dx squared. By the way, this dx is 1 unit, so I don't need the parentheses around it. And I have dx squared. So this is actually d dx times d dx of x cubed. And I hope that you can see in the notation that that is the first derivative that you have to do, and then there is another derivative in front. So now, copy d dx, and when you take the inner derivative, what do you get? You get 3x squared. And now, clearly, there is another instruction to take one more derivative, which will be 6x. And that's what, so you can see that you can still do this in line rather than writing 3 separate lines. You see, over here we have a line for the function, line for the first derivative, line for the second derivative. So that's 3 lines to get to the answer. If you are using Leibniz notation with inline writing, you have the whole thing like this. And that's it. I'll see you Tuesday. Yes.
Can you just back up, go through the previous example where you did the square root of x, the derivative of that, one question quite like that.
No question. Can I move it real quick? Or
But he's using it now.
it? Yeah. Okay. Well, I gotta show one bottom for the other one. I'll take one.
Okay, what happened?
The derivatives of the square root of x. Minus 1.
Yes.
Could you skip the step in there?
Well, I wrote it here,
Oh,
x to
okay,
the 1/2,
okay.
right?
All right.
So that's the 1/2 that drops,
Right. Okay. Now
and then 1/2 minus 1 is negative 1/2, right?
see
Okay.
that.
I don't know. Here's what you financing. I have a question. So I just want to clarify. So how you got the second derivative? 6 is that 6 is in front of the derivative, right? X equals 0.
Yeah.
Because it's a constant. 1 is a constant, so that'll be 0. So 6 plus 0 is 6.
Yes.
Okay.
Sorry I was loud for today. I'm just exhausted.
All good. Go home and sleep.
Yeah, I had the bell holes today.
Yeah, they're good. Oh my
Yeah, I
God,
mean-
the invasion.
But it's in the pocket. It gets crammed with everything else. And it's hard to pull it out. But
Plus, it rubs against the keys, it scratches the
Exactly.
yeah.
this one's also easy to get to.
Yep.
That was not okay.
That was awesome.
And my test.
No.
I did my
So
test.
Yes.
we,
Okay. So,
we did something, but
all right. See you
Have a good
soon.
weekend.
where I so I
Have a good weekend.
You too. I'll see you next week.
And you changed the due dates for the 3
I did already.
The door. So if somebody turns and looks, his face is right here.
She was standing literally this close to the door. It was really entertaining for everyone except. Promise no recommendation letter ever.
Oh my God.